Okay, so we're going to talk about an introduction to enzyme kinetics, or kinetics. First we need to talk about the rate, or velocity, and this is essentially the change in the concentration of a reactant or product, and I'm writing this backwards now that I say, or reactant with time. So units for rate or velocity are going to be molarity for concentration per second. The rate constant is a proportionality constant, or a proportionality between the reaction rate and the concentration of the reactants. If I can squeeze that in there. So we can say that the rate is proportional to the reactant concentration. That being said, K then, which is our rate constant, equals the rate in molarity per second divided by the concentration of that reactant, and that is the molar concentration. So the molarity units cancel, and our rate constant, or K, will have units of 1 over S, or S to the minus 1. Next definition is for a rate law, and this expresses a relationship of the rate of the reaction, and I'm going to now just abbreviate reaction Rxn, to the rate constant and the concentration of the reactants. And these will be raised to some power. Okay. So we can take a look at a generic example. So if I have A moles of reactant A reacting with B moles of reactant B to give me C moles of product C plus D moles of product D, my rate constant, or my rate law, is going to equal my rate constant times the concentration of A raised to some power times the concentration of B raised to its power, whatever that might be. X and Y are experimentally determined. And that's done by using data collected through the course of the experiment with respect to changes in concentration over time. Okay. The order of the reaction or the reaction order, we could call it, is the sum of the powers. That are assigned to those reactant concentrations. Reactant RXT concentrations. Okay. And they, obviously, those are the exponents that are appearing in the rate law. So let's take a look at a first order reaction. And this is when we have reactant A being converted to product P. We can write a rate expression that gives us the change in the concentration of A over the change in time. This is negative because A is a reactant. It is being converted to product. The rate law would equal then K times the concentration of A. So we can set these equal to one another and say that the change in A over delta T is equal to K times the concentration of A. That was concentration there. We can express this graphically, but first let's take a look at a different form. Whoops. So this is a combined rate law. And so from this expression, should pop down here, sorry, we can say that the ln of A at time t divided by the concentration of A naught, which is A initial, is equal to negative KT. And essentially, this then we can also rearrange, and we can say then that the ln of the concentration of A at times t equals negative KT plus the ln of the concentration of A initial, or A naught. So this gives us the form of y equals mx plus b. So we can then plot a linear relationship where the slope is negative k, the y-intercept is ln A naught, and we're plotting against ln concentration of A at t versus time. There is also a half-life equation for a first order reaction. I didn't write that, but first order. And that's all we'll be concerned with. The half-life for a first order reaction is T1/2 equals 0.693 over K. So you have some problems associated here. We're going to omit A plus B going to P plus Q, or 2A going to P. But for 2A, we are asked to determine K, or the rate constant, and we were given the half-life. So K equals, we've just rearranged this equation. So K equals 0.693 divided by 20 minutes. Now, if you encounter a problem that has time units other than seconds, it is fine just to leave them in those units. You don't have to convert to seconds. So we have a rate constant of 3.47 times 10 to the negative 2, 1 over minutes, or min to the minus 1. In the next problem, I'm going to go to flip to a new piece of paper. You are asked to find, I believe it is, because I don't have it in front of me for some reason, the amount of time it takes to convert 20% of A or our reactant to product. And, yeah, I'm sorry, I do have it. What is the time to form 20% of product? For this, we need to use ln of A at times T, T, divided by the concentration of A naught equals negative KT. We are looking for, and we must have been given the rate constant. Oh, we calculated that in A, never mind. So we're looking for T. So we need to define what the concentration of A is at time T and A initially. So concentration of A naught, I am going to say is 1, or it could be 100. And at time T, we have converted 20% of A to product. So we have 0.80 left of A. So now we're just going to plug our numbers in here. So we're going to take the ln of 0.80 divided by 1.0. I guess I don't need that. And that equals negative K, so negative 3.47 times 10 to the negative 2 min to the minus 1 times T. So we'll just rearrange and solve for T, and T equals a negative 0.223 divided by a negative 3.47 times 10 to the negative 2 min to the minus 1, and my time then equals 6.43 minutes. So keep in mind that time is never going to be negative, so that will help you keep track of signs in your calculations. And in C, we are asked to calculate how much of A remains after 15 minutes. So we are still going to use a variation of that equation. So we're looking at the concentration at time T when T equals 15 minutes, and we have negative KT plus the ln of the concentration of A naught. Now, I'm going to continue to say that A naught equals 1. So the ln of A at T is equal to negative 3.7 times 10 to the negative 2 min to the minus 1, and that is times 15 minutes plus, ln of 1 which is 0. So the ln of A at t equals a negative 0.5205, and taking the inverse of that, we get e raised to the minus 0.5205, which equals 0.594, or 59% of A remains after 15 minutes.